I thought it'd be useful for us to go through some more practice problems together. So let's start here with a cyclopentane ring, and we're going to put two methyl groups on it, and we're going to have them both wedged. We can go through and figure out the R and S for each side. Okay, we're going to get an R and an S here actually for this one. If I put my hydrogen back, you can use your right hand here, and you're going to see that this side is 1. I like to put my number right on top of the bond. It helps me make sure I organize it 2, and then 3 right here on the methyl. And you can use your right hand. Another little trick is this hydrogen is going back. If the lowest priority, number 4, is back behind the paper, you can simply use an arrow and draw from 1 to 2 to 3. Notice my arrow is going clockwise, and that's always R. Or you can use your right hand. Okay, it depends on what works for you. The only problem with this method is then you always have to make sure number 4 is going back. So feel free to keep using that hand method that I also taught. Let's draw the mirror image of this on the left side here. We would simply switch the stereocenters. Now, as we look at this, okay, we can go ahead and label R and S for this as well. So if I'm looking at this center here, I've got my methyl going back. That means I have my hydrogen coming forward, okay? I'm going to label this side 1. You can go through your Kahn-Ingold Prelog priority. And then I have 2, and then I have a methyl here, that's 3. Okay? If I use my right hand, it's going to be opposite. So this one will now be S. Okay, so I have a stereocenter of S. And you can do the same thing for the right side, and you're going to end up getting R. So it kind of looks like we went, this one's RS and this one's SR. So nominally, it looks like they could be enantiomers, but they aren't, and that's because of this internal plane of symmetry. So really, any time that you're questioning if something, is it an enantiomer, you need to look for the plane, if they have a plane of symmetry. Okay? If it does, then you need to notice here that these two compounds are actually the same. And this is a meso compound. Meso compounds are these pesky compounds that look like enantiomers, but they actually are the same. Sorry I drew this here. I'm going to erase it. So you might want to scroll down on your piece of paper. We're just going to redraw this cyclopentane structure, and we're going to look at a couple other relationships with it. There we go. So for my cyclopentane structure, I'll just redraw it here. Let's go ahead and draw. Let's draw a diastereomer of this one. Okay, so a diastereomer would just have one of these centers switched. Right? So we have R, S, okay? This stereocenter didn't change. This one is now R, okay? Let's draw another diastereomer. I'm going to switch this one, okay? We have SS, okay? So we've tried to draw the enantiomer of this first one, and we found out that it's actually meso. So let's just describe the relationship between these 3 cyclopentane structures I do have. Again, we're using these terms just as relationship statuses, I guess. So the relationship between these 2 compounds, if we look at them, only one stereocenter changed, RS to RR. That means these are diastereomers. You can probably hear Rhodey in the background. Okay, the relationship between these 2 are also diastereomers. Only one of the stereocenters switched. Okay, and the relationship between these 2 compounds, what is that relationship? We're going SS to RR. I used a different color because you're right. These are enantiomers. Both switch. So remember, enantiomers all switch. It's not just Typically, we just see enantiomers with one chiral center, but you can have as many as you want. As long as all of them switch, they are enantiomers. Okay. Notice here that this compound has more than one relationship status. It's enantiomers with this compound, but it's a diastereomer with this RS compound. All right. So remember that these are just terminologies we use for relationships between molecules. Let's go over some examples. This slide might look a little like, whoa. Okay, we're going to go back. I want you to open up your notes to the page where we talked about the process in which we decide the relationship between molecules. So the first question was always, does it have the same molecular formula? So let's do this first one. Does it have the same molecular formula? Yes, has an OH group, has a methyl, has a cyclopentane ring. Bingo, we're good to go. Does it have the same connectivity? Why, yes, it does. We have this carbon here, and there's the methyl, the OH group, and the cyclopentane ring. The next question here that we asked on that sheet was, are these non-superimposable mirror images? Well, they aren't mirror images because there is no actually chiral center, okay? These two molecules are actually the same. Notice here, this side and this side are the same. So if you were to even try to write R and S on this, you couldn't, okay? If I take this molecule and I just simply flip it over, okay, I would get this compound. This is why I taught you R and S first, because it's probably one of the fastest ways to check to see, all right? If there's no R and S, they are definitely not enantiomers. We draw this on the piece of paper showing the OH coming forward. Okay, and now the OH is going back on this side, but there's no chiral center. That means there's no mirror image. These two molecules, the relationship that you would write for them is simply same. These are the same molecules. Okay, now they aren't meso because there are no chiral centers. Meso have chiral centers, okay? Just remember that. Meso have chiral centers and a plane of symmetry. They have to have both. These organic chemists and their freaking terminology and names, right? Okay, so if it doesn't have a chiral center and they're connected the same and the molecular formulas are the same, these are the same molecule. Let's go to the next one. This example here is kind of a trick question. First question, do they have the same molecular formula? Yes. Are they connected the same? No, they are not. It'd be really easy on an exam to look at this and start to try to analyze your R and S. If they aren't connected the same, you can just simply write, hey, these are constitutional isomers. And then you say, nice try, Dr. Miles. Moving on. Okay, let's go to the next example. Okay, cool. Now I come back to the whole connected the same. Do they have the same molecular formula? Yes. Do they have the same connectivity? Yes. We have this carbon here. This is a chiral center. We have a methyl, chlorine. We have this sulfur alkyl group and a hydrogen. Cool. 4 different things. Here's another chiral center. The next molecule has the same connectivity. Let's go through and look at the relationship here. So in this first example, you could go through R and S on this, and I highly suggest that you practice if you're still having trouble with R and S. But I'm going to show you a way to just look at this and understand the relationship. This carbon here has a chlorine coming up towards us. Okay, the geometry that I've drawn this in, this conformer, is the same as on the right. Okay, notice the bent structure is the same. The only difference is this sulfur group. So we've only switched one of the chiral centers. I'm going to circle this chiral center in green. Okay, so there is only one switch. If at least one of the stereo centers is switched, okay, and the others are the same, these would be diastereomers. I want us now to do a quick little practice problem. I want you on your piece of paper to take this compound. I'm going to draw a box around in blue, okay? And I want you to draw its enantiomer. We should have room right here. Okay, draw the enantiomer of this. one of the easiest ways to do this is just to switch both. Bingo, enantiomer finished. Both chiral centers are switched. All right, okay, so what happens when we have this Newman projection here that I have on the top right? So for this example, what I like to do is I like to draw out my wedge and dash line form. So let's just go ahead and label our carbons. So we've got a 1 and a 2. So here's our 1, here's our 2. 3 is going back behind the paper, and then coming down would be 4. Okay, cool. So when we do this, we know that the two groups that are on one side of this Newman projection will be on the same side of our molecule, meaning that they're both going to be wedge or dash. So let's just choose one. In this case, it doesn't matter when we choose because this is dependent on how we rotate this Newman projection. You might want to build yourself a model kit if this is still challenging for you. So the chlorine and the methyl are going to be on the same side. On carbon 2, I have this methyl. Okay, so I'm just going to put a wedge on carbon 2. Let me rewrite my 2. I've lost it. And then on carbon 3, this chlorine is on the back carbon. So I'm going to put this on a wedge. Cool. Now we're going to go to the right side, and let me just put a box here. I'm going to say that this is dash. This has to be opposite of the left side. Again, you could build a model to help you see this. On carbon 2, I have this proton here, okay? And that makes sense that it would be back, okay? And the only position left on carbon 3 would also be back. And that's really where that ethyl group comes in. Let me redraw 3 right there. Okay, so now we have our line and dash structure. So let's draw the next one. So here we have carbon 1, 2, 3, 4. And I didn't really walk through this. I just assumed they had the same connectivity and molecular formula because I was the one that made up the examples, and I knew they did. But you would want to make sure of that first. And sometimes it's easier when you draw this line, wedge, dash structure, okay? So carbon 1, carbon 2. So carbon 2 didn't change. It still has the methyl coming forward, and it still has that hydrogen going back, okay? The only difference here is carbon 3. Look at this chlorine and this ethyl relationship. These two differ in that realm. So the chlorine here is on the right side of the Newman projection, and it's on the left side on this other one. Now, if I draw these in, then you'll see that these two, whoops, I meant to use green on that. These two are going to be dash. So we still use the same wedge and dash when we compare two Newman projections that have the same molecular formula and connectivity. You could switch it, but then that would make it more complicated to try and rotate. So in this case, we're going to have the chlorine going back. That means the ethyl here is coming out towards us. Now, do we have a chiral center? It's sometimes hard to see with the Newman projection, but I think it's easier with this line, wedge, dash formation. Do we have 4 things bound on this carbon? Negative. We have 2 methyls. Okay, do we have 4 things bound on this carbon? Yes, we sure do. Okay, that means that we can figure out R and S for this. Now, you could just stop here and say, cool, these are my 2 chiral centers. They both have the same connectivity, molecular formula. They just differ in space. There's only one chiral center, and that chiral center is obviously switched. So at this point in time, you could write enantiomers, and you could move along your merry way on the exam. If you aren't convinced with your assessment, you could go through and label R and S to convince yourself that these are indeed enantiomers. There's one chiral center, and that means that that chiral center has to be switched. If I look at carbon 3, my lowest priority here is going to be my methyl, and it actually has a 4 on it, but I'll draw 4, okay? My next lowest priority would be my ethyl group, okay? This would be 3, okay? The next would be this isopropyl. It's an isopropyl because there are 2 carbons attached here. This would be 2, and the chlorine would be 1. If you put your thumb where the methyl is at, the lowest priority, I'll highlight this again in red. That's the lowest priority, okay? The left hand does not work, however, your right hand does. So look at your thumb over to the methyl, and then notice your hand is on chlorine, and you rotate, and you hit 2 and then 3, okay? You might need to build this in order to kind of see that more. This would be R. We can do the same thing on the right side here. If you put your thumb where the methyl is at, you're going to actually see that you need to use your left hand in order to do this. Chlorine is the number 1 priority. The second would be the isopropyl, and the third would be the ethyl group. If I put my left thumb where the 4 is, your finger should be starting at the chlorine. It'll rotate, hit that number 2, the isopropyl. And if you were able to rotate your fingers more, you would come up and hit the ethyl. So this one would be an S. So that's another way to check to see if you have enantiomers. Find all the chiral centers, see if they all switch. Okay, let's do the last example on this slide. That's getting nice and full. All right. And I might be writing more than you need. I'm just trying to show you more than one way to solve some of these. So let's look at this cyclohexane structure. I have 2 chiral centers here. It's what it looks like, right? And then it looks like I've switched both of them. What do you notice, though, about this structure? Well, it has a plane of symmetry, doesn't it? That means I should be able to take this, and it should be the same as this. All right, let's think about this. If I look at this cyclohexane structure, if I flip it over, both of these groups will, in fact, go dashed. So even though there are chiral centers, because of this plane of symmetry, these 2 compounds are the same compound. You can take this cyclohexane structure and flip it over, and both of them would then be flipped, right, upside down. It's this plane of symmetry that is causing this to not be enantiomers. They look like they're enantiomers. Both centers are switched. If it has a plane of symmetry, they are not enantiomers. This is a meso compound, and it's just a term we say about this compound. It has chiral centers, but it has a plane of symmetry. That means it does not have an enantiomer. The thing that looks like an enantiomer is not an enantiomer. It's actually the same. So this is a meso, and these would be labeled as the same compound. Also, you would say it's a meso compound in particular. I want to talk about one more thing, and it's this terminology when we use enantiomers or diastereomers in reactions. So let's do our one reaction that we've learned. We're going to take an HX, and we're going to add it across an alkene, okay? So we know that the proton is going to be on the carbon with the most protons, and that means that we're going to get our bromine here on the carbon with the least amount of protons. Now, we know that we form a carbocation here in the reaction. I'm going to pick up a proton. The bromine is going to be left as Br minus. I have a carbocation, my proton added here, and I have Br minus. By now, we've drawn this a few times. It's really good for us to practice mechanisms because that's all you're going to be doing in Chem 345, a whole lot of mechanisms. So when we draw this, we know that carbocations are flat. Remember that we can add the bromine on the top or the bottom. That means that we also get this structure. What's the relationship between these 2 molecules? They are enantiomers. Instead of drawing this as a product, you could also draw the reaction as follows. Gives you this product, and you can write the word racemic. By drawing one of the enantiomers and writing racemic, remember racemic means a 1-to-1 ratio of R and S, okay? So for the answer for predict the product, you could write both of them, or you could just write one and write racemic underneath it, okay? All right, so what happens, how are you able to get diastereomers in reactions? And let's look at that. So in order for you to get a diastereomer in the reaction we were talking about, you're going to already need a chiral center present on your molecule. And the starting material here, we would label this as optically active. Some professors might just write the molecule and they'll indicate if writing this means that you only have one of the enantiomers. Saying optically active means that you have the majority of the enantiomer that is drawn. This one here, if I draw in my hydrogen, okay, we could label the R or S here. If I label my priorities, this is 1, this ethyl is 2, and the methyl is 3. Okay, the hydrogen's going back, so I could actually just draw an arrow here. See, it's going clockwise. You could also use your right hand and see that this is indeed an R. Clockwise gives you R, or your right hand here gives you R. All right, you have an R enantiomer, and it's optically active, meaning that's the one you have right here to start the reaction with. If you react this with HBr, now we know this mechanism pretty well. You're going to draw what didn't change. There is no chemistry that happened on this side of the molecule. Remember, this reaction only happens at the alkene. So you don't change this. The center did not change. Now we draw in our bromine here that was added. In the case of this example, you're going to need to draw both products. That's because these are diastereomers. If you had drawn and wrote racemic, that would actually mean that you also have the following structure. Remember that racemic is talking about enantiomers. And we know that enantiomers, all of the centers change. So let's look at this here. So if all of the centers change, right, that would mean that this molecule would be what is meant when you say racemic. Okay, notice here that, notice here that that this center on the left, it also switched, but we did not do any chemistry there. No chemistry occurred at this R stereocenter. It remains unchanged. And we know this because we know the mechanism. We know the mechanism doesn't change that stereocenter. So for a reaction like this, what you want to do is if you get the diastereomers here, you start with something optically active, okay? And then we made a new stereocenter, and we know that this stereocenter could be both ways because it went through a carbocation. You would need to draw both. Only if you have enantiomers, like this example, can you just draw one and write racemic. Okay, so again, be really careful when you use the word racemic because it could be wrong. This would be not correct. The answer that I have above, where both are drawn, is the correct way to show the product for this reaction. Now, Rhodey wanted me to share one more thing with you. She said I made one of the quiz questions a little too hard, but really it's right in line with what we're trying to talk about right here. So if you're watching this, guess what? We're going to talk about the quiz question. This is one of the quiz questions where you had this alkene, the cyclohexene derivative in the presence of HI, and you were asked to write the product here. Let's go over the mechanism. So we've got the alkene is going to pick up this proton, okay? You're going to use a reaction arrow showing the reaction is going forward. Here, I have this carbocation that's formed, and I have I minus. This is going to attack this carbon. And the product that we get, though, it has both a methyl and it has an iodine here. Now, for the answers that you could choose, two of them might seem kind of confusing. Based on what I just drew, there's only two possible answers here. One of them has this product drawn and it says racemic. The other answer that has this same connectivity has not optically active drawn. Hopefully by this time in the videos, this makes sense, but I wanted to go over it. So when I say racemic, this is assuming we have an R and an S, okay? This is kind of a trick question. There is no racemic for this molecule. In fact, it would be totally correct to draw this on your paper on an exam. And why is that? Well, this carbon is not a chiral carbon. If you don't have a chiral center, you can just draw all of the bonds as lines. Line drawings essentially are just saying it doesn't matter if it's wedged or dashed, okay? By showing that on the bottom here, I say that it is racemic, this is one of the answers. So possible answers. When I say on this answer, if I write racemic, this is saying I have an R and an S, but we have neither R or S because there's no chiral center. So, whoops, centex, geesh, center. So this would be incorrect. By saying it's not optically active, this means that there's no chiral center on this, okay? And also it means there's no enantiomer enrichment, right? There wouldn't be because there isn't a chiral center. See how that's kind of a trick question? Like I said on an exam, drawing it flat like this without any wedges and dashes is fine. You could also draw it with the wedge and dash and don't write anything there because simply drawing it as it is means that there isn't a chiral center. Organic chemists are supposed to be able to look at that and say, oh yeah, like that's the same as if I were to flip this molecule over, right? So then the iodine would be up and the methyl would be back, and these are the same. Okay, so there's no chiral center, there's no mirror image. I wrote not optically active to try to help you understand that that drawing is in fact not optically active. So the one here on the right is the correct answer for the quiz. So Rhodey, you can thank Rhodey for asking me to go over that. I don't know where she went. Rhodey. That was really nice of you. Also, we can't be giving out quiz questions all the time. You're not going outside.